When a matrix is symmetric, it can be orthogonally diagonalized. What that means is we can find this type of decomposition where the eigenvalues are going to be all real and the eigenvectors are all orthogonal to each other. Now, this only occurs when the matrix is symmetric. Now, even more is that we can then write our matrix as a series of projection matrices. So effectively what happens is that when a matrix acts on a vector, what it does is it simultaneously projects that vector onto each of those eigenvectors and then sums them all back. Now that's great, but that requires your matrix to be symmetric. So what about if our matrix isn't symmetric? Well, then the nice benefits start to go away. We will be able to get eigenvalues if the matrix is square, but there's no guarantee that the eigenvectors will be orthogonal, and the eigenvalues could be complex. Now, even worse, if our matrix isn't square, then we don't even have eigenvalues and eigenvectors. They're not defined. But something amazing that happens here is that we can get something similar to lambdas and v's, so eigenvalues and eigenvectors, for any matrix, whether it's symmetric or not, whether it's square or rectangular. So what is this? How do we get something useful? And it all stems from the fact that we've got this observation. If I take a matrix A, and let's say it's m by n. Now, just to try to put things into a bit of a geometric perspective here, this transformation is going to map Rn into Rm. So when our matrix has n columns, that means that the input vector has to have the same number of entries. So here, the vector lives in Rn, and this is, you can think of as the input space. And then Ax is a vector that lives in Rm, and that's going to be the output space. So the idea here is that we're going to take this matrix, it's rectangular, and we're going to form this product, A transpose times A. So we'll call this matrix G. Now, if you take the transpose of G, you can apply transpose properties. The transpose of a product is the product of transposes in reverse order. So you'll get something that looks like this, A transpose A. Well, guess what? That's symmetric. So G is symmetric. And as soon as G is symmetric, that tells you that G has an orthogonal diagonalization. Now here, the dimensions of G, they're going to be n by m times m by n, which means that G is an n by n matrix, and that means that all of these matrices will be square, n by n. V is going to be an n by n matrix that is orthogonal, and it holds the eigenvectors of this matrix G, and D is a diagonal matrix, and it's going to hold all of the eigenvalues down the main diagonal, and they're going to correspond there. Now that's great. Nothing new, nothing surprising, but it's a way for us to connect any matrix into something that can be orthogonally diagonalized. Now, a couple of notes, right? If G has eigenvalues and eigenvectors, that means we should be able to write it like this, which we're going to say. Note 2, we can always organize our eigenvectors so that lambda 1 will be the largest one, lambda 2 will be the next largest, and we'll go down all the way to lambda n. These are going to be greater than or equal to 0 because G is symmetric. And remember, part of the orthogonal diagonalization is that you have to have real eigenvalues. And finally, the third thing we should note here is that lambda I could be 0. And if that's the case, that means G would be non-invertible. Why? Because if you were to take the definition of an eigenvector, if you have a zero eigenvalue, that means you have a non-trivial solution to this homogeneous problem, which means you are not invertible. So all of those things aside, we are going to assume that G has R non-zero eigenvalues. And so when we list them like this, lambda 1, lambda 2, all the way down, lambda R will be a non-zero number, and then all the others will all be 0. Because in general, we don't know how many of them could be 0. We want to allow for the possibility that some could be 0. Now, all of that aside, what we're going to do is we're going to talk about this matrix G, and I know that it has this orthogonal decomposition. What we're going to talk about now is something slightly different. Remember, G came from the matrix A, so we're going to talk about this dot product, AVI and AVJ. And for now, we're going to assume that they aren't necessarily the same value. Now remember, V is a matrix in Rn, is a vector in Rn, and A is an m by n matrix. So this product, AVI, is going to live in Rm. It has to be in the output space. So if we take a look at this, there are a lot of wonderful dot product properties that we can use. Remember that a dot product could be written as a product of matrices if you use the transpose. And again, using the transpose of a product is the product of transposes in reverse order. So we can write things like this. And because it's a matrix multiply, we can regroup these brackets however we'd like. And this is going to be key because now this thing here is our matrix G, and G is going to be applied to an eigenvector. And when G is applied to one of those eigenvectors, this produces the eigenvalue times the vector, which we could pull out, write this product as such. And so what this is going to tell me is I'll have lambda j vi dot vj. And essentially that's how this game is going to work. What am I going to do with this? Well, there are 3 really useful things that I can pull out of this. So number 1, if I and j are the same, that means that I'm going to get the following. AVI dotted with itself is the square, or is the length of that vector squared. And we know that the length always has to be a positive number. At the very worst, it's equal to 0. So that's one way to interpret this. And from above, we know that this has to be equal to lambda I times vi dotted with itself, which means that this is lambda I times the length of this vi squared. But we know this has to be 1 because these are all orthonormal vectors. That's the thing you get when you have an orthogonal orthonormal decomposition. And so the point of all of this is we can see that all of these lambda i's have to be greater than or equal to 0. They all have to be non-negative. Now, at the very worst, they're going to be equal to 0. Okay, so once again, if I is equal to j, then what we've got is that the length of this vector squared is equal to lambda I. Now we know that this is greater than or equal to 0 from above. And that means that if we just wanted the length of this vector, it's going to be the square root of this lambda I. Now we're going to make a definition. We're going to call this thing sigma I. And this is going to be called a singular value. And that means that this length of this vector, AVI, is equal to this sigma I, a singular value. It's related to the eigenvalues of the square matrix, but just coming back to this, this is what we want. Now note, if these lambda i's are equal to 0, so if we happen to be in one of these eigenvalues that is 0, that means that the length of our vector will have to be 0, which implies by length properties that this has to be the 0 vector. Okay. So again, what that means is that A is not invertible. Okay, so that's the second property. Now the third property is going to be what takes us forward a little bit. If we compute this dot product and these two vectors aren't the same, remember that when we've got our orthogonal diagonalization, we've got two vectors that come from their two eigenvectors. They have to be 0. And that means that if we go way back to this product up here, we had AVI dotted with AVJ. We found that it had to be equal to lambda I, VI dotted with VJ. And if those things are orthogonal, that means this has to be orthogonal. So what this is telling me is that all of these output vectors, AVI and AVJ, these are all orthogonal. So what we get is this set, AVI, AV1, AV2, all the way down to AVR. These are orthogonal. Actually, I shouldn't say VR. It goes all the way down to the end, VN, because we have a full set of vectors there. So just to kind of recap, we took a matrix. It was rectangular in general. We saw that when we took this product, A transpose A, we produced a symmetric matrix. That means that the symmetric matrix can be orthogonally diagonalized. It has n orthogonal eigenvectors. We can normalize them, and it's got real eigenvalues. So if we piggyback off of that, we can take a look at the products AVI. So we can see how the matrix A is going to act on those particular vectors. When we put it all together, we find that those particular vectors are orthogonal. We can normalize them. And if we normalize them, we're going to say that U1 is AV1 over its length, which means that it's AV1 over the first singular value, or AV1 is equal to sigma 1 U1, if you want to think of it like that. U2 obviously would be AV2 over the singular value, and we're going to proceed down until the very last non-zero singular value. So this is the smallest non-zero singular value. And once we get to there, then that's all we can do in terms of normalizing. But what we've got is the following. So that means that this thing, AV1, or sorry, I should say U1, U1 all the way down to UR, this is an orthonormal set in the output space Rm, but it is not a basis for Rm. We have too few vectors. But that's not a big deal. We can extend by using the Gram-Schmidt process, and we can add additional vectors, and they'll all be orthogonal to create a basis for Rm. So that means U1 down to UR, those are the ones that we got from the matrix. We can just find some new ones all the way down until UM. That's okay. We're allowed to do that because the Gram-Schmidt process lets us do that. So here's what we've got. We can put it all together. And what this is going to do is have some information about A pop out for us. We've got these AV1 equals sigma 1 U1 all the way down to AVR equals sigma 1 UR. And after that, we've got these AVRs. AVR plus 1 is 0, and that'll go all the way down to the very last one. They're all 0. And we're going to organize this as, instead of a vector equation, a system of vector equations, we're going to organize this as a matrix equation. And here's how we're going to do this. So as a matrix equation, you'll be able to see here that you've got this AV1, AV2. We're going to set equal all of these vectors as entries in a matrix. So that's where that side's going to come in. And then on the other side, we need to figure out what we're going to write down. Now, before we get going, this, by definition of a matrix product, is going to be this. And you should be able to see that this is the product A times V. Now, A is our original m by n matrix, and this was the n by n orthogonal matrix that we got from the orthogonal diagonalization of G. So that's fine there. Now, on the other side, what we've got is something that follows. So on the other side, we've got this. We've got a sigma 1 U1, sigma R UR, and then a bunch of zeros. What I'm going to do is define the following. I'm going to define this matrix capital U. It's going to be U1 all the way down to UM. These are an orthogonal. This is an orthogonal matrix, and it holds an orthonormal basis for Rm. And so that means that on this left side, we've got AV. Now on the right side, I'm going to do something suggestive here. So I'm going to have a U. And in order to get this to pop out, what I'm going to have is I'm going to have a column vector with m entries. And they're going to be this first singular value all the way up top, zeros. Second entry here is 0, sigma 2, 0, all the way down. Now, once I get to the R, I'm going to have that sigma R, the last non-zero one. Then the remaining columns are going to look like this. I'm just going to slide this over. Then the remaining columns, I'm just going to be weighting with zeros. And that's going to go right to the end. So if I wanted to, I could write this as another matrix times matrix. And here's how it's going to look. The first column here is going to be a sigma 1 with zeros all the way down. Sigma 2, zeros all the way down. And this is going to go to sigma R, zeros all the way down. And if I wanted to, I could think of this now as a bunch of zeros remaining here. So this is going to be an interesting matrix. Now up here, this matrix here is m by m because it has to be a basis for Rm, so there needs to be the right number of them. And this thing here I'm going to call capital sigma. And this is some m by n, and I'm going to call it a diagonal matrix, even though it can't be diagonal because it's not square. And this has the singular values down the diagonal, and then it's got some zeros everywhere else. And what this lets me do is come up with the following. AV is equal to this U sigma. And because V is orthogonal, I can multiply it on the left with its transpose, because the inverse is that for an orthogonal matrix. And what I'll end up with is the following result. For any matrix A, I will have this. And this is something called the singular value decomposition. I take my matrix m by n for any matrix, any size. This is going to be an m by n orthogonal matrix. What it does is it has an orthonormal basis for Rm, the output space. V is an n by n orthogonal matrix. It holds an orthonormal basis for Rn, the input space. This thing sigma is another m by n, and I'll call it air quotes diagonal matrix. It holds the singular values.